Hello, and welcome to my talk on the behaviour of compact three-planet systems before and after an instability event. I'm Pete Bartram from the University of Southampton, and this is a collaboration with my co-authors here in blue. The main focus of our talk is to present results from stability experiments of compact three-planet systems, but instead of terminating simulations upon the first close approach, we continue all the way to first collision of planets. We've chosen to look at analogues of our own solar system, which are also consistent with masses of compact systems found in the Kepler dataset. Integrations are performed of a solar mass star being orbited by three Earth mass and Earth radius planets on initially circular coplanar orbits. We wish to determine the effects of initial orbital spacing upon the collision probabilities of systems. So to this end, we choose initial separations that are evenly spaced in units of mutual Hill radius of adjacent planets, thereby ensuring that the period ratio of the inner and outer pairs of planets are identical. We parameterize the separation between planets via the term beta, such that the semi-major axes, A, can be determined from the equation shown. Experiments are performed over the range beta equals 3.464 to beta equals 8.15, with a density of 1000 runs per unit beta, and the orbits of these two extremes can be seen in the plots on the right hand side. The initial longitudes are also marked on these plots with a red cross, and time throughout is specified in orbits, and that is relative to the initial period of the innermost planet. Results are shown for systems with the innermost planet located at 1 AU, but we've also generalized these results to include data at 0.25 AU as well. As a metric for instability, we choose to use the time of orbital crossing and denote it as TC throughout. Likewise, we integrate all the way to collision of planets, which we call the impact time, and we denote this as TI. If no collisions take place, we terminate at 1 billion orbits. We have, however, had to terminate some runs after 10 to the 8 orbits to save on computation. All integrations are performed using the Terrestrial Exoplanet Simulator, TESS. That's with a single S. TESS is a new, non-symplectic special perturbation method that follows Brouwer's law for over 1 billion orbits. The plot at the bottom shows this, where for all of our 4,000 plus runs, only one system experienced an energy violation above 10 to the minus 13. As TESS is an unknown quantity, we also performed identical integrations using Rebound and Mercury, where we found very good agreement with results. And we are planning to open source TESS shortly. In this figure, we plot the impact times in blue and the crossing times in orange with respect to initial orbital spacing beta. We see that the increase in crossing times with increase in initial orbital spacing as expected. We perform linear fits to beta and to the log of time and find that TC model has a slope of 1.345 beta, which strongly agrees with previous works, and this increased our confidence in our tool. We also fit a model, the same model, to the impact time, and find that the slope is shallower with a value of 1.087 beta, owing to the impact time being large in proportion to the crossing time for lower beta. Impact times are obscured by the scale of this plot, but we will recover them later. Interestingly, we also find a number of systems, which are marked here in green, where systems collided without first experiencing an orbital crossing. In this plot, we show the probability of collision over time for various beta ranges. Systems initially located at 1 AU are shown with solid lines, and those at 0.25 AU are shown with dashed lines. We see here that the collision probability for smaller systems is higher at a given point in time, but also that this effect is lost in comparison to the lifetime of systems at higher beta. In this figure, we show the time that systems survive after an orbital crossing against the initial orbital spacing, beta. We find three populations of survival times: those below a tenth of an orbit, which experience collisions immediately after a crossing; those below 2 orbits, but greater than a tenth of an orbit, which experience a close encounter, become bound, and then collide a fraction of an orbit later; and finally, those that experience an orbital crossing, separate, survive for at least another 10 orbits, but with a median survival time of roughly 1,000 orbits, depending on beta. We find a weak dependence between the survival time and beta, with a slope of log TS proportional to 0.14 beta, and we find the longest surviving runs last for slightly less than 1 million orbits. The colouring on this plot is used to indicate which pair of planets was involved in a crossing and a collision. There's only 3 possibilities here, as crossings can only occur between the inner or outer pairs of planets. Therefore, blue indicates the same pair being involved in a collision and crossing. Orange indicates the pair colliding was not the pair that crossed, whereas green indicates a collision between the innermost and outermost planets. We find that the short-lived populations of systems after a crossing are almost exclusively between same pair runs, and the probability of same pair planets colliding remains highest for several thousand orbits, at which point chaotic mixing eventually takes over and collisions between other pair and extremer pair become equally as likely. So just to summarise, we've shown a dependency between the survival time after crossing and the initial orbital spacing beta. We find that there are 3 populations of behaviours after a crossing. Those that experience immediate impacts, those where the close encounter that causes an orbital crossing causes 2 planets to become bound, which then collide a fraction of an orbit later, and those that do not experience a prompt collision. We've also shown that collisions are much more likely between pairs of planets that initially experienced a crossing. And that's it for me, so thank you very much for listening.